Have you ever stopped to think about what a sound really is? What's actually happening? Well, today, we're going on this incredible journey. We're going to follow the life of one single sound wave, all the way from a silent, invisible vibration to the digital code that lets you hear this right now.
So, to really get a handle on any sound, you have to look at its spectrum. Think of it like a sound's unique fingerprint, or maybe its DNA. It's the special mix of frequencies that gives it a character all its own. And this spectrum, well, it's the key to everything that happens to it, from the second it's born to the second it hits your ear.
Okay, so here's how we're going to break this down. It's a three-act story. First, we'll see how a sound is born from vibration. Then, we'll follow it on its journey through the world. And finally, we'll look at how we can shape it and capture it. So let's get started with Act 1.
All right, Act 1. Every sound you can possibly imagine, from the quietest whisper to a massive explosion, it all starts in exactly the same way, with a vibration. But, and this is the whole secret, it's the way something vibrates that gives each sound its own distinct personality.
This brings us to a really cool idea called resonance. You can think of it as an object's favorite frequency to vibrate at, its happy place. The swing analogy here is just perfect. You know how when you push a swing at just the right moment, at its resonant frequency, it goes higher and higher with barely any effort? In the world of sound, that same principle gives you a louder, clearer, and much more powerful tone.
And this is exactly why some sounds linger so beautifully, while others are just a quick thud. A tuned object, like a bell or a wine glass, doesn't have much friction holding it back, so it just keeps on vibrating for a long, long time. On the other hand, a damped object, like say this wooden table, has a ton of friction, so that vibration just dies out almost instantly.
And get this, it's not just solid things that resonate. Air can do it too. When you blow across the top of a bottle, you're actually making that whole column of air inside vibrate at its favorite frequency. It creates this super stable pattern of pressure called a standing wave, and that's what produces that cool, distinct pitch you hear.
You know, this uncovers a kind of secret formula that applies to so many sounds. Whether it's your vocal folds vibrating and being shaped by your throat and mouth, or a guitar string vibrating and being amplified by the guitar's body, the principle is identical. It's always a two-part system, something that vibrates and then something else that resonates and gives that vibration its final character.
So, our sound wave has been created. It exists, but its life is really just beginning. Now it has to travel through the world. And that's a journey filled with obstacles that are going to bounce it, absorb it, and bend it, constantly changing what we end up hearing.
So, the first thing our sound wave is up against is just simple distance. As it travels outward, its energy gets spread thinner and thinner. This means sound gets quiet shockingly fast. That drop of 6 decibels every time you double the distance, that's a huge loss of power. It's the reason why someone shouting from way across a field sounds so much quieter than someone whispering right next to you.
Okay, so now imagine our sound wave is just rocketing through a room. It's colliding with everything, the walls, the furniture, maybe even you. And every single one of these collisions carves and shapes the sound, building up the incredibly rich and complex soundscape that we're all living in right now.
So every time our sound wave meets an object, it has to make a choice. If it hits a hard wall, it reflects, it bounces right off, creating an echo. If it hits something soft, like a heavy curtain, its energy gets absorbed, literally turning into a tiny bit of heat. And if it hits the edge of something, it can actually bend around the corner. That's called diffraction, and it behaves just like an ocean wave bending around a pier.
Okay, now imagine you're not getting just one echo, but thousands upon thousands of them all bouncing off every surface in a room. This super dense, chaotic storm of reflections is called reverberation, and it is exactly why you sound so amazing when you sing in the shower. You're not just hearing your voice, you're hearing your voice plus 1,000 copies of it all arriving at your ears almost at the same time, blending into this big, powerful sound.
And that brings us to our final act. The sound wave's journey is almost over. It's no longer just the victim of its environment. Now, the tables have turned. We get to take control, using technology to sculpt its personality and, in the end, capture it forever.
Filters are basically the sculptors of the audio world. They give us the power to precisely control that sound fingerprint we talked about, its spectrum. You do this all the time. When you turn up the bass on your stereo, you're just using a low-pass filter to let the low rumble through. And when you crank the treble, that's a high-pass filter. You're basically performing sonic surgery.
You know, every filter has its own unique sonic signature. It's called its impulse response. That sounds technical, but it's basically just the sound the filter makes when you hit it with a really fast click. The sound it makes in return tells you everything about it. For example, when you gently tap a wine glass, that clear ping you hear? That is its impulse response. It's revealing exactly how it's tuned.
Now, this is a really critical distinction. A linear system is like a perfect photocopier. What comes out is an exact copy of what went in, just maybe louder or softer. But no new frequencies are ever added. A nonlinear system, though, that's like a broken photocopier. It adds its own random marks and smudges. It fundamentally changes the signal, creating brand new frequencies that weren't there to begin with. And we have a word for that: distortion.
So finally, the big moment. We capture our sound wave. To take a smooth, physical wave and turn it into digital code, we follow these 3 steps. First, we sample it. We measure its pressure thousands of times a second. Then we quantize it. We give each of those tiny measurements a number. And last, we encode it. We store that huge sequence of numbers as binary code, just ones and zeros. And just like that, the physical wave is gone, replaced by a perfect digital file we can copy and play back forever. And that's it. Our sound wave's journey is complete. From a simple vibration through a complicated world of reflections and absorption, all the way to its final digital capture. So now, when you hear the echo in a big concert hall, or the muffled sound of a voice through a wall, or that awesome crunch of a distorted electric guitar, you know the physics behind it all. You now have the tools to hear and understand the secret life of the sounds that are all around you.